guys, in today's video we'll be talking about problems based on design of reinforced concrete beams. This video will be mostly about simply supported beams. So this is the question. A reinforced concrete beam is to be simply supported with bearings of 230 mm. The clear span of the beam is 6 meter. The beam has a width of 300 mm and a superimposed load of 12 kN per meter. Use M20 grade concrete and Fe450 steel. First thing we'll write down is the given details. With support, that is the bearings, means that is the supports of the beam, that means the width is given to us indirectly, 230 mm. Clear span is 6 meter, or you can write it in millimeters, it's 6000 millimeter. B is equal to 300 mm. FCK is equal to 20 Newton per mm square, which is M20 grade. That is the characteristic strength of concrete, and the characteristic strength of steel is Fy 450, that is equal to 415 Newton per mm square. Next we write the live load, that is 12 kilonewton per meter. Next we check the calculation of effective. The clear span is given to us. Now we have to check the depth. When we calculate check how to calculate the steps of a beam, the first thing we write the given details, then next is we plan the value of the depth. So for simply supported beams, it has to span by D is less than 20. Span by D is less than 20. That is, the L by D is equal to 12 to 15. That is, D value should be within the range L by 12 to L by 15. That is 500 to 400 or 400 to 500. And I have taken 450 mm. You can take any type of value. It has to be within the range. Now I'm going to assume an effective cover of 50 mm. So we can calculate the overall depth. 450 plus 50 is equal to 500. Effective depth is the depth till the center of the reinforcement. We have to calculate the total beam as well, since we're designing the whole beam. So overall depth D is equal to 450 plus 50, which is equal to 500 mm. Now we calculate the width. After the depth, we'll calculate the width. It has to be given that the width is 300 mm, so we don't have to calculate it separately. Now we calculate the effective span. Effective span is equal to clear span plus depth. That's the first formula. 6000 plus 450, which is 6450 mm. Effective span is equal to clear span plus width of the support, that is the second formula, and we get 6230 mm. Now we take the minimum value, that is 6230 mm. Okay, now we calculate the ultimate. Now how to calculate the self weight of the load, that is dead load. Dead load is equal to rho into B into overall depth, and we get 3.75 kilonewton per meter. Live load is already given to us, and hence we add it up and get the total load. Total load is equal to 15.75 kilonewton. After, now we have to find the ultimate load. This is the actual load given to us. We have to convert it to point load. That is the ultimate load. That is, we have to multiply it with the factor of safety, and we get 15.75 into 1.5, which is equal to 23.625 kilonewton. Now next we calculate the moment of resistance which takes place when the load is imposed. Here the load is uniformly dispersed. It does not mention whether it's under reinforced or balanced, but the load is uniformly distributed here, and it is also simply supported. So what is the formula for the moment of UDL? In simply supported case, it's WUL square by 8, where L is the effective span used here, and we get 114.61 kilonewton meter. Now for Fe 415 grade of steel, mu limit formula, that is mu limit by FCK BD square is equal to 0.138. Mu limit is equal to 0.138 into 20 into 300 into 450 square, and we get 167.67 kilonewton meter. Here mu less than mu limit, so it is safe. Now we know it's an under reinforced section. Now we have to calculate the area of steel. In under reinforced section, we know that mu is equal to 0.87 Fy AST D into 1 minus Fy AST by FCK BD. Okay, so we substitute the value in the mu formulae and we get it in a quadratic equation. And after we get it in a quadratic equation, we solve it. The quadratic equation we got is 25.19 AST square minus 162,472.5 AST, which is equal to 114.61 into 10 raised to 6. And we get two values, and we take the minimum value here. That is, since the stirrup spacing between the main reinforcements has to be kept a minimum, so we take the minimum value of the area of steel required, so 806.17. So AST required is equal to 806.17 mm square. This is the area that the moment of resistance acts upon the tensile reinforcement. Now with this required area, we have to, it is not necessary in the required area, the number of bars that takes place area should also be that much. It can be less or more. So with this AST required, we can calculate the number of bars. So we assume the diameter to be 20 mm since it's not given in the question. Number of bars is equal to AST required by area of 1 bar. So 806.17 by pi by 4 into 20 square, which is equal to 2.566. We can approximate it to 3. So there are 3 bars. Now we find AST provided that means that's the area that these bars are it's the area that has to be provided for these bars to be incorporated in a beam. So AC provided is equal to 3 into pi by 4 into 20 square, that is 942.47 mm square. Now we check the minimum reinforcement. Now we have to see whether it is safe. First we check the minimum area, that is AST by BD. In section 26.5.1.1, page 46 in the code, we have a formula for AST by BD, that is equal to 0.85 by Fy. We substitute it and we get AST minimum, that is 276.506 mm square. Next we find the maximum area. AST max is equal to 0.04 B into overall depth, which we get as 6000 millimeter square. It satisfies the condition AST minimum less than AST provided less than AST max. Hence this design is safe. Now next we design shear reinforcement, obviously, because when we place tensile reinforcements to hold the tensile reinforcements in place, we put shear reinforcements, not only that, to prevent cracks. Now first we find the shear force. First we find the actual shear force value. So here we will be using the actual load, that is 15.75, which is a total load. Total load is the actual load. The ultimate load is point load that we multiply with FOS. So first we find the actual shear force and we get 49.061 kilonewton. Then we find the ultimate shear force that we require, VU, which is equal to V into 1.5, 49.061 into 1.5, which is equal to 73.591 kilonewton. Next we find nominal shear stress. Tau V is equal to VU by BD and we get 0.545 kilonewton per millimeter square. Next we find percentage of steel. PT is equal to 100 AST by BD, which is equal to 0.698%. With this percentage of steel as well as the value of the grade of concrete, we find the shear stress of concrete. which is by interpolation method from code ISO 562,000 table in table 19. Why? Because the value is in between two PT values as well as two grades of concrete. The shear stress value will be between two grades of concrete. So we use interpolation method and we get x equal to 0.503 Newton per mm square. That is tau c value, and tau c max is equal to, that is the maximum shear stress that the concrete can handle, is equal to 2.8 Newton per mm square. This one we get from table 20. Next, we check the condition tau v is greater than tau c but less than tau c max. That is nominal shear stress, that is a shear stress imposed on concrete, is greater than the shear stress of concrete. Hence, what's going to happen when this happens is that we have to there will be inclined cracks that's going to take place. So we have to provide additional shear reinforcements. Now we have to find the shear force of the additional shear reinforcement, that is VUS. So we find shear force of shear reinforcement. VUS is equal to VU minus VUC, which is equal to VU minus tau C into B into D. And we substitute the values, we get 650.5 Newton. Now next we find the spacing. To find the spacing we have to provide the stirrups. We provide 8 mm 2-legged vertical stirrups. You can provide 4-legged or 6-legged, but since 2-legged is simple, we will only be requiring 2-legged here. So 2-legged vertical stirrups of 8 mm. The diameter value of vertical stirrups varies from 6 mm to 16 mm. So I'm taking 8 mm. SV is equal to 0.87 Fy ASVD by VUS. We find ASV, that is the area of vertical stirrups, since there are two legs, 2 into pi by 4 into 8 square, which is equal to 100.53 mm square. And hence we get the spacing, we get a large spacing, 25,100 mm. Next we check the condition for minimum spacing. In my previous video I mentioned before, when we find the spacing of vertical stirrups, it has to be kept minimum, else chances of maximum bending will take place and there will be a crack in the middle. So to avoid that, we decrease the spacing. So there's a condition for it, maximum spacing, that is the first one, 0.75 into D. We get 337.5 mm. Second is 300 mm. Third is the value we found, and we take the minimum value, that is 300 mm. Okay, so we got the minimum value as 300 mm for spacing. Hence we provide an 8 mm 2-leg vertical stirrup at 300 mm cross section. Now we find the minimum reinforcement for stirrups. We have found the minimum reinforcement, tensile reinforcement, right? We found the in the maximum and minimum range. To find the minimum reinforcement for stirrups, ASV minimum should be greater than or equal to 0.4 B into SV by 0.87 Fy, and we got 99.70 millimeter square. Hence ASV provided is greater than ASV minimum, hence it is safe. Now we check for deflection. Since we found the effective span and we apply shear stress, the chances of deflection is there, right? So the condition is that L by D, that is L effective by effective depth, should be less than 20 into K1 into K2 into K3. Since it is a singly reinforced beam, K2 equal to K3 is equal to 1. Now we have to find K1. Now how do we find it? We can find the steel's service loads value, that is Fs equal to 0.58 into Fy into AST required by AST provided. Now we found the Fs value 206. In figure 4 of IS 456-2000, there's a graph in which y-axis is the modification factor and x-axis is the PT value and the curve is Fs. We have curve and the PT value. We draw a line from the PT value, that is 0.698, to the curve, that is 206, a particular point in the curve 206, that will be in. After that, from the curve we draw another line to the y-axis and we get the value of modification factor. which is 1.3 approximately. Now L by D less than 20 into 1.3, we see that 6230, we substitute the value 6230 by 450 should be less than 26, which is 13.844. That means it is less than 26, hence it is safe. Okay, now we find the value of development length. LD is equal to 0.8755 for toe BD. Now this is actually to increase the tensile reinforcement strength, else chances of slipping is more. Now toe BD value is 1.2. Why? In the question, live load and dead load is good. Live load and we found dead load, right? Those are tensile loads. In the IS code, bond stresses, that is toe BD values, in tension is already given in the table, which for grade 20 it's 1.2, and we get development angle 1504.375 mm. Hence next will be, last but not the least, detailing. This is how we draw the detailing. This is the longitudinal part, and that at the side is the side part. 450 mm effective depth and 300 mm width, and here 3, 5, 20 mm main reinforcements are used here, and 2 left 8 mm stirrups at 300 mm cross sections. This is how we write detailing, and 6.23 is the effective span, and 6 meter is the clear span, and 500 mm is the overall depth. Okay guys, so that was all for today. I hope you understood today's video how we design RCC simply supported beam. So with this, I'm going to conclude here. Thank you.